Alright, here we're going to start our discussion on electrochemistry. Electrochemistry and oxidation reduction go pretty much together. I am not going to spend that much time on oxidation. You should already know how to assign oxidation numbers. You should already know how to balance redox reactions. If you are not strong in those two areas, please plan to come see me before A period, during brunch, during lunch, or ask questions during class. But again, you should know how to assign oxidation numbers and balance redox reactions, either by the half reaction method or the quote-unquote shortcut method. Either way, you get the same answer. So a few things of terminology to start with. Oxidation, just remembering that is the element becomes more positive in its oxidation state. So for here, sodium as a solid goes to sodium ion plus an electron. Remember, all elements in the elemental state have an oxidation number of 0. Reduction, the oxidation state becomes more negative. So we are gaining an electron and going from chlorine, which is 0, to chlorine ion, or 2 of them, to keep everything balanced. An old memory device for oxidation and reduction goes like this. Remember Leo the lion? Leo says grrr. That's right, I said it. Loss of electrons is oxidation, and gain of electrons is reduction. And it happened twice. I don't know. Another way to remember is oil rig. Look at the letters. Oxidation is lose. Reduction is gain. Again, talking about electrons. So Leo says grr or oil rig. Either way, you should be able to remember what's going on. Our third one is oxidizing agent. Now remember, oxidizing agents themselves are reduced. So because the oxidizing agent is reduced, it causes something else to be oxidized by taking its electrons. And the opposite, the reducing agent, is itself oxidized. By it being oxidized and losing electrons, it's causing something else, another element or substance, to be reduced. And our last one is the anode. Place where on the on a battery, the electrode where oxidation occurs, and the cathode, place on a cell where reduction occurs. So a memory device to help remember the difference between anode and cathode is red cat. Reduction happens at the cathode. Another part of this device has been an ox red cat, anode oxidation, reduction cathode. So in a spontaneous cell or galvanic cell, the reduction is always at the cathode and oxidation is always at the anode. Hence, an ox red cat. Here's our table of reduction potentials. I suggest that you print one out off of my website, go into the downloads page, and get it. This is the one that is used on the AP test. This one here is not a complete one. The one on my website will be complete. Couple things to note here. Everything is measured against hydrogen. So hydrogen is arbitrarily given a value of 0. So combining everything to see what happens, they get the reduction potentials in volts based on hydrogen. The more positive the value, that half reaction will proceed as a reduction. The more negative the value, that reaction will proceed as an oxidation if combined with something that has a more positive reduction. So again, more positive leads to reduction, more negative, when combined with something else, leads to oxidation, and the reaction will be flipped. So here's a cell. On the right-hand side of it, you can see there's a reduction of hydrogen. On the left-hand side, we're looking at the oxidation of zinc. And this is they're measuring it against the standard hydrogen. Again, as we said, they're measured against hydrogen ion reduction, which is arbitrarily assigned a potential of 0 volts. Why is it assigned arbitrarily 0 volts? I don't actually know. Sorry about that. But I figure hydrogen is the simplest one, easiest one to work with. Could be. I could be wrong. So this is your kind of standard galvanic cell. Anode is on the left with a negative sign. Cathode is on the right with a positive sign. Electrons flow from negative to positive. And then your volt reads should be a positive value. So our galvanic cell. Galvanic is the main one you're going to see. It is a spontaneous process. So all galvanic cells are spontaneous, meaning that the cell potential, E naught, is going to be a positive value. They use some other weird looking E with a little squiggly line at the top. I couldn't find the symbol. Sorry. But your textbook uses that one, and everything else is going to use that one, but I'm just going to use E. Sorry. Therefore, a negative free energy is associated with a positive cell potential. So here we have yet a third indicator of a spontaneous process. Delta G predicts spontaneity, entropy predicts spontaneity, and now cell potential predicts spontaneity, because they're all kind of intertwined. Again, let's look at the chart here. Anode on the left, cathode on the right. Electron flows from left to right. Note the negative sign on the anode and the positive sign on the cathode. Just like your car battery, black and red, anode, cathode, everything's the same here. The porous partition, or sometimes could be a salt bridge, allows to keep the charge balanced on either side within the cell. So certain ions are able to flow back and forth, not electrons, but ions, nitrates, sulfates, some type of ion that can go back and forth, and as more positive is built up on one side, the negative ion moves over there, and as less positive builds up and back and forth. So if we look at the zinc copper galvanic cell, we see that zinc is going through the oxidation and copper is going through a reduction. We have zinc sulfate, copper sulfate solutions. So notice the zinc ion is heading towards the right, the sulfate ion is heading towards the left as the cell proceeds, then the balance of charge. One thing to note here, when a battery is quote-unquote dead, this process has reached equilibrium. So the cell potential will be 0. Again, when a battery is dead and the process stops, it has reached equilibrium and the cell potential is 0. So from the table of reduction potentials, we see that zinc and copper are written like this. Notice that copper has the larger positive. Therefore, copper must proceed as a reduction, and zinc must proceed as a oxidation. So, since we have to flip the direction of the arrow with regard to zinc, we also have to flip the algebraic sign of the cell potential for the half reaction of zinc. So as we said, less positive, more negative, and here we go. Zinc has been flipped, and the cell potential of zinc went from a negative 0.76 to a positive 0.76. And then the overall cell potential, you just add them up. So the easiest rule of thumb when you're trying to figure out the cell potential of a galvanic cell, switch one to be the oxidation, switch its algebraic sign, add the two values. The book goes into reduction minus cathode and all this crazy stuff. It's just easier to flip the sign and add. If you forget to flip the sign, you're going to be making mistakes. So, line notation. This helps us to abbreviate what's going on in a electrochemical cell. So looking at this one, you always look at the species being oxidized, species being reduced, are separated by a double line in the middle. So one side is the anode material, and the other side is the cathode material. So material solution on the oxidation, and the material and the solution on the reduction. If there is also different electrodes, so in this diagram we have zinc metal being an electrode and copper metal being an electrode. Because they're the same as everything else, they're not written in the line notation. However, let's say we used platinum wires. Well, before, on looking below at the white letters, before the zinc, there'd be another single line, and before that, you'd put platinum. And after copper, on the right-hand side, another single line, and you'd put platinum. So if you use something other than the material that's being oxidized and reduced, you will usually include that as part of your line notation. I don't think line notation even really shows up on the AP test. I don't remember them asking for it on a FRQ. Maybe multiple choice it might ask you. But obviously you need to know which one's oxidizing, which one's being reduced. It's pretty straightforward. So, calculating Gibbs free energy for a cell. So through this equation, which I believe is on your equation sheet, delta G naught equals minus NFE. So E naught from the reaction previous gives us our 1.10 volts. N is always going to be moles of electrons in the balanced redox equation. Going back to, you have to be able to balance a redox equation in order to figure out the number of electrons. F is Faraday's constant. I think your equation sheet calls it 96,500. So just go with that on the equation sheet. You don't have to go with this number. Go with what's on the equation sheet. And then cell potential is cell potential. Did that one again. I don't know why. Plug it all in, and then you can solve for delta G in kilojoules, and you have what you're looking for. So there you go. Notice this is a negative value because cell potential is positive, delta G is negative. This is a spontaneous reaction. You put them together in an electrochemical cell, it's just going to happen. The Nernst equation. This is probably the fundamental equation for electrochemistry. Interestingly enough, it has been removed from AP Chem next year. I don't know why. They're idiots. Who knows? I'm kidding. So the Nernst equation looks at the standard potentials assuming concentration of 1 molarity. So the E naught, just like delta G naught, has to do with standard conditions. With regard to electrochem, standard conditions is 1 molar. The following equation does allow us to calculate when they're not 1 molar. So if it is 1 molar, you can just use cell potential, how we just solved it before. When they're not 1 molar, use this equation, which I do believe is on your equation sheet. R is the gas constant, temperature in Kelvin, moles, and Faraday's constant, again on the equation sheet, 96,500. They rounded for some reason. Okay. So if you're at 25 degrees, the Nernst equation gets simplified a little bit. 25 degrees is also standard condition. You can use this reaction, you can use this equation at any temperature, but when it's 25 degrees, it kind of simplifies a little bit. Notice we have, in this equation, natural log of Q, but in this one is the regular log of Q. You can look at your book for a derivation of what's happening, but here's the equations to help us solve it. So, let's now relate equilibrium constant and cell potential. So, at equilibrium, we know forward and reverse reactions occur at equal rates. Therefore, the battery is dead. So, a battery or electrochemical cell, when it has reached equilibrium, no more electron flow, cell potential is the cell not potential, little 0 on the top, is going to be 0. So we know that this is 0 volts. Modifying the Nernst equation at 25 degrees, we get this. I lied. The cell potential is at 0. E naught is always going to be a number you can solve for based on the half reactions. But the cell potential itself will be 0. Again, E naught is based on half reactions, which doesn't really matter if the cell is moving or not. We want to know what it's going to be. So plug everything in, rearrange a bunch of stuff. So plug that in. Again, you can do some math and solve for K. And here we go. Notice the value of the equilibrium constant. Is this product favored or is this reactant favored? That's kind of an obvious question. But it makes sense that the equilibrium lies extremely far to the right. So when the battery does reach equilibrium, it will have gone to the right pretty far before it finally stops. Now, cell concentration, when both sides are the same component but different concentrations. Just another variation of type of questions they could ask you. Obviously, zinc is going to be both reduced and oxidized. However, different concentrations are going to drive this reaction in one direction or the other. Again, we got to get to 1 molar. So we want to determine which side undergoes oxidation, which side undergoes reduction. Well, the 0.1 molar has to increase, the 1 molar has to decrease. We want to get them to the same concentration, or if we could, get them to 1 molar. In this situation, we're probably going to get somewhere in between. So 1 molar has to decrease in concentration, so it's going to have to be reduced. Therefore, the 0.1 molar has to be oxidized. So they got to get to the same concentration. And you can figure out based on what's happening, if I have to reduce the amount of zinc, or zinc ion, I have to reduce it. And if I want to increase the amount of zinc ion on the other side, I have to oxidize it. So you get this. Here's your reaction. Obviously, they are the exact same reduction potential. So if you look up the values, you're just going to get 0 anyway for this cell. So calculating it from the Nernst equation, we have this lovely thing again. Continuing on, we know E naught is now 0 because it's the exact same reaction except, oxidation and reduction of the same thing. We know there's 2 electrons in the transfer. Q, our reaction quotient, still plays a role because we're not at equilibrium. We're solving for Q to figure out which way we're going. Plug everything in, and you get your answer. So the cell potential during the process of this reaction is going to be 0.030 volts. All right, the electrolytic process. Electrolytic process is the opposite of a galvanic process. Notice in this diagram, the negative and the positive have stayed where they are, but the anode and the cathode have switched. Also at the very top, use an external battery source, meaning you are forcing the electrons in the reverse direction. Well, if you have to force the electrons in the reverse direction, does that mean this is spontaneous or not spontaneous? Not spontaneous. Good. So, electrolytic processes are not spontaneous because you're forcing it with an external power source, usually a battery. We have a negative cell potential, which means what is delta G going to be? Correct. Positive delta G. So again, electrolytic processes are the opposite of galvanic processes in that the anode and the cathode are switching sides. So anode is still oxidation and cathode is still reduction, but the electrons are flowing in the opposite direction compared to that of a galvanic cell. The electrolysis of water in acidic solution, for example, looks at, here's the anode reaction, here's the cathode reaction. We have water being split apart into hydrogen and oxygen for a negative 2.06 volts. This is not a spontaneous thing. You have to force this to occur. There is an external source doing it, a battery, plug it into a wall, something to force it in the reverse direction. All right, electroplating of silver. Hopefully a lab we're going to do is we're going to copper plate a nickel. It's always a fun one. Looking at what's going on here, again, another source of current, so there should be a negative cell potential. We have silver nitrate and some other stuff floating around here. Water, is acid, hydronium ions in there. So silver is being oxidized. Silver is also being reduced, but obviously on different sides. You need a solution of plating material, which is usually made with 18 molar sulfuric acid. Anode made of the plating material, so it usually helps to have a silver bar. Quite expensive. When we do ours, we're just going to use copper wire. Cathode with the object to be plated. So usually we take more copper wire and just wrap it around the nickel and then turn it on and it goes. And then a source of current for our purposes in the lab, we'll use a 9-volt battery, which works quite well. Well, of course, if we're going to be plating something, if I start with an object with nothing on it, and then I end with an object covered in another material, I want to know how much material I actually added onto it, or I want to find out if I added X number of grams, how long did it take? So here's an example, solving for how many seconds it will take to plate out 5 grams of silver on from a solution of silver nitrate using 20 amp current. So we know our reduction is this. So 5 grams divided by the molar mass gives us moles of silver. Then the mole ratio of electrons per mole of silver is a 1-to-1 from the reaction. Then we have to use Faraday's constant, coulombs time divided by moles of electron. And then amps are the same thing as coulombs per second. So here this cancels out. And now it's going to take 2.2 times 10 to the 2 seconds to plate out 5 grams of silver of solution. Notice here you can go both directions. If they gave you time, how many grams did you plate? Looking at this couple things here, this is amps or coulombs per second. This is Faraday's constant, coulombs per mole of electrons. Here's your mole ratio for stoichiometry. Here is molar mass. And then here's the amount that you're trying to solve for. Either way, you should be able to go both directions with this. And we have finished our electrochem discussion for now. Please go to the locker and you can start looking at the worksheets for electrochemistry. The first, I think, 2 or 3 of them have to do with assigning oxidation numbers, balancing redox reactions. So please take a look at that, and I'll see you in class on Monday.